Hello everyone, I'm Dr. Chris Lewis, and this is my first video of the course. You've already watched a few videos and might be asking yourself, what can you offer me, Dr. Lewis? Well, I'll tell you. Do I have mnemonics? Yes. Do I have high-yield teaching? You betcha. Do I have pathology slides? Heck yeah, I do. And that's not all. I have a bunch of hats that I might wear. Well, not this one. This one's dumb. And I've got these super cool pink future glasses and these highlighters, which may not be much use for you directly, but they're still pretty awesome. So strap yourself in, because with all this stuff, you and I are gonna kick some step one butt. Ah! No, more explosions. Well, that was weird. Hello everyone, and welcome to our Step 1 video on cellular suffering and death. Oh, it sounds so sad, but exciting. So first let's talk about apoptosis. So apoptosis is an orderly cell death process. And when we say orderly, we mean that we expect and actually plan for this cell death. Now it is a natural and needed process that serves to get rid of cells that are no longer of any use. So why is apoptosis so important? Why do we need a complicated process to allow our cells to die? That should be easy, right? Well, if we let cells die in an unorganized manner, all these cell contents would spill out and would then produce an inflammatory response, which is not ideal. So we have developed a process by which these doomed cells are broken up into small kind of bite-sized pieces, which are then phagocytosed by other cells with no messy debris floating about, and most importantly, no inflammation. So, what causes apoptosis? Well, there are physiologic situations and pathologic conditions. So the physiologic causes will include things like during embryogenesis, so we don't all have 12 fingers or a bunch of tails. Cell breakdown during menstruation is another example. And there's also proliferation cell populations in the body, like immature lymphocytes that we need to get rid of and go through that programmed cell death in order to maintain a constant cell number. And then there are pathologic causes, DNA damage to a cell through radiation or hypoxia, misfolded proteins that occur due to gene mutations or exposure to free radicals. Infections like HIV will induce cells to undergo apoptosis. Now you need to know the descriptive histologic characteristics of apoptosis. So what are we going to see? Well, first, most cells are going to shrink. Also, something called pycnosis occurs. So, what's that one? Well, pycnosis is condensation of the nuclear chromatin, which then kind of results in a shrinkage of the nucleus, and this actually causes the cell to look basophilic. You'll also see something called membrane blebbing. You'll also see karyoresis, another weird word. That's just nuclear fragmentation. You're also going to see a formation of apoptotic bodies, so things are kind of breaking apart into smaller pieces, which are then again phagocytosed. Again, no inflammation is taking place with apoptosis. You're not going to have kind of the red, hot, warm area that is classic of that inflammatory process. So with apoptosis, you have the cytoplasm, it's blebbing away, it's being taken care of by phagocytes, the cell is shrinking bit by bit, and again, no nasty inflammation. So now we get to the tough part of apoptosis, the mechanism. Now before we get too far into the specific pathways of apoptosis, I want you to know that the ultimate initiators of apoptosis are a family of proteins called caspases. Now they exist in an inactive form in cells, and then when they're cleaved, they become active, and then they carry out many important functions associated with initiating apoptosis. So that's just the end of the story. Caspases equal apoptosis. Now, I wish that was all you needed to know. Let's go back to the beginning of the story and talk about the pathways. Now, the two pathways are the extrinsic and the intrinsic pathway. First, let's talk about the intrinsic pathway. So this is the major mechanism of apoptosis, and it's used for both the physiologic and the pathologic conditions that are going to lead to this. It's also referred to as the mitochondrial pathway because it involves an increase in mitochondrial permeability, which leads to the release of pro-apoptotic molecules. So let's get into this. So BCL2 is a family of proteins that closely regulate the permeability of the mitochondrial membrane. Now, mostly they act as an anti-apoptotic protein. Now, if there is DNA damage or another apoptotic signal is received, then another family of proteins called the BAX or the BAX will go into the mitochondrial membrane and create channels that allow the contents of the mitochondria to flow out. So let's review. BCL2, anti-apoptotic. BAX, or BAX, is pro-apoptotic. Now, one way to remember this is that BCL2 has 4 letters and/or numbers, and LIV, or live, has 4 letters. BAX has 3 letters, and then also die has 3 letters as well. And BAX also rhymes with axe, so BAX is giving axe to cells. That's the way I remember it. And again, that BAX is letting the contents of the mitochondria out. So what's in the mitochondria that's so bad for cells? Well, the answer is cytochrome C. Cytochrome C will then start a cascade of enzyme activations that will end up activating caspases, which we talked about earlier before, and that again is going to lead to apoptosis. So next, let's talk about the extrinsic pathway. So you can remember this because the signal is coming from outside of the cell. And there's actually kind of 2 different mechanisms here. First, there are the death signals. In the cell membrane, there are 2 different receptors that can receive those death signals. And this includes the TNF receptor and the FAS receptor, also referred to as the CD95. So they will be activated by either TNF alpha or by the Fas ligand, respectively. Now, once activated, the receptors will transmit signals that will again cause activation of caspases. Now, another extrinsic mechanism occurs when killer lymphocytes, mainly cytotoxic T cells, recognize a cell as foreign or infected. So these lymphocytes will then release perforin and granzyme B. So what do? Well, perforin will punch holes in the plasma membrane. Remember, perforin will perforate. That's the way I remember that one. And then that granzyme B is going to enter into the cell and activate the caspases directly. All right, so let's go over this again in a Lewis Notes. Hello everyone, welcome to our very first Lewis Notes, and Lewis Notes are what we're going to use some throughout this course in order to really knock home some of our highest yield stuff. So what I like people to do is break out their own piece of paper and write in some of this stuff yourself, because the more you put it into your brain, especially if you're writing it, the more likely that you are to retain it. So we're going to do a matching game, and you'll see me do a lot of matching games throughout the course. So here we're looking at our intrinsic and extrinsic, and we boiled it down to the most important stuff, and we're going to do a matching game here. So let's start with the intrinsic pathway here. So first we have the anti-apoptotic stuff. Remember, anti has 4 letters in it, so that's going to be our BCL2, and we're going to put that right over there. What about our pro-apoptotic stuff? Remember, that's going to be our 3-letter one, so that's going to be BAX. So if something activates BAX, then you're going to start this whole cascade down. So if you get BAX that's stimulated, you're going to get an increase in what? Remember, this is going to be the increase in mitochondrial permeability. And you don't want to do that, because once you get mitochondrial permeability up, you're going to start spewing cytochrome C all over the place, and that's going to lead to further initiation of apoptosis. Now let's move over here to the extrinsic pathway, and first we have our death receptors. That sounds like a cool band name. So our death receptors, the first one we have here is the TNF receptor, and if that gets stimulated, then you're going to run into problems. The other one that you need to remember is the FAS receptor, also known as CD95. Now, the other way that the extrinsic pathway can work is through killer T cells, so those cytotoxic T cells, and it's going to use things like perforin. Remember, you're going to use perforin here, and that's going to put holes in the plasma membrane. Then the plasma membrane is wide open for granzyme B to sneak on in. That granzyme B is going to go enter in the cell, and it's going to lead to activation of caspases, and then those caspases are going to then promote apoptosis. So if you can remember all that stuff right there, then you're going to be good to go on the intrinsic and the extrinsic pathway. Now, one last mechanism of apoptosis that maybe doesn't fit in either pathway is protein P53. So P53 is a very important player in DNA repair. Now, if DNA damage is present, P53 will arrest the cell in stage G1 of the cell cycle. So this will actually allow time, it's just stalling, for the DNA to be repaired by repair enzymes. Now, if the damage is irreparable, then P53 will then activate mechanisms that will then again lead to apoptosis. Now, P53 is often referred to as a tumor suppressor protein because if P53 is dysfunctional, then this can lead to tumor formation in cancer. All right, so now let's move on to necrosis. So necrosis is cell death that is not orderly. So everything we try to avoid in apoptosis tends to occur in necrosis. Now, all the intracellular components are spilling out into the world, and as you would expect, this causes inflammation. Now, there are several types of necrosis that you should be aware of. Now, most of the descriptive terms refer to their microscopic appearance, but we also see this necrosis and these types of necrosis in specific organ groups as well. So the first one is coagulative, and coagulative is characterized as kind of a gelatinous substance in dead tissue, and it occurs in the heart, in the liver, and the kidney, and it occurs in low oxygen environments, so maybe after an infarction. Next, we have liquefactive. So this is a viscous liquid mass that occurs more in the brain and very often and commonly in bacterial abscesses and pleural effusions. Infections cause an inflammatory response that is going to lead to this type of reaction. Next, we have caseous necrosis. So this is a kind of a combination of coagulative and liquefactive, and it tends to look like kind of clumpy cheese. It's really nasty. So this is seen very commonly in tuberculosis, systemic fungal infections as well. Next, we have fatty or fat necrosis. This results from the activation of lipases and can be seen with pancreatitis, can also be seen in subcutaneous tissues as well. Next, we have fibrinoid necrosis. So this is in blood vessels, so think vascular things. So this is caused by autoimmune or just immune-mediated vascular damage. And then we have gangrenous necrosis. That can be either wet or dry. We'll go into great detail of that in a future lecture. The wet version is seen with bacterial infections. It's common in extremes. I always think of like Civil War injuries and having to cut off limbs with saws with that type of gangrene. There's also a dry version, and this is seen with ischemia, and it occurs in the toes and the feet. And it's mainly due to arterial occlusion. You'll see those really nasty, like black toes. All right, so we've established that necrosis is messy and cellular contents are spilling into the body. If you suspect pathology in certain organs or cells, then you can test for these contents or markers to see if cell death is occurring. So we're going to look into the study guide here. What cellular byproducts might you detect in the serum when the following cell types are injured? So let's talk about cardiac first. So cardiac myocytes, when they die, what are you going to get? We're going to get things like myoglobin. You're going to get CK, CKMB. You're going to get troponin I. So when someone comes to the ER with chest pain, we always check for cardiac enzymes, especially troponin I and CKMB. Now, what about with skeletal myocytes? What if they die? What are you going to see? Well, you're going to see an increase in CK, aldolase, again, myoglobin. In patients with rhabdomyolysis, muscle breakdown, is going to release massive amounts of myoglobin, which is actually going to be toxic to the kidneys, so you can end up with renal failure. What about hepatocytes in the liver? If you have a lot of liver damage, you're going to see an increase in AST and ALT, alkaline phosphatase, and GGT. If you have damage to salivary glands, you're going to see an increase in amylase. If you have problems with the pancreas, you're going to see increases in amylase and lipase. If you have RBCs or red blood cell damage, you're going to see heme, which will then break down into bilirubin, and that'll be elevated. All right, so let's talk a little bit more about cell injury. It's important to know the different characteristics of cell injury and what those characteristics of reversible cell injury or an irreversible cell injury. So with reversible cell injury, which is usually correctable with sufficient oxygen and nutrients, this is characterized by things like decreased ATP synthesis, cellular swelling, nuclear chromatin clumping. But be aware that sometimes that chromatin clumping can also be seen with irreversible injury as well. You can also see this with a decreased glycogen, a fatty change of the liver or of the cells. So you might see this in hepatocytes if you go maybe binge drinking or if you have a Tylenol overdose. Also ribosomal detachment resulting in decreased protein synthesis. Now, the characteristics of irreversible cell injury, injury that your cells can't come back from, are things like the nuclear pycnosis, the irreversible condensation of the chromatin. You can see karyolysis, the complete dissolution of the chromatin. Karyoresis, which is the fragmentation of the nucleus. You can also see this with calcium influx causing caspase activation, plasma membrane damage, lysosomal rupture, increasing mitochondrial permeability. Again, all irreversible cell injuries. And then next, I want to cover briefly some of the types of cell injury. What are the major culprits when it comes to damaging our cells? So the first one is ATP depletion. So without ATP, really nothing works. The major causes of ATP depletion are reduced supply of oxygen and nutrients, mitochondrial damage as well, and actions of even some toxins like cyanide. What else can cause our problems? Mitochondrial damage. We talked about this a little bit before. So this is closely related to our first mechanism because mitochondria are the suppliers of our ATP. Ultimately, this will impair ATP production. Now, the mitochondria have an outer and an inner membrane, and that houses several proteins that are capable of activating apoptotic pathways. So remember, we already talked about how those cytochrome Cs can activate caspases in the cytosol. Therefore, if you damage the mitochondria, then you might signal apoptosis and that programmed cell death. Now, mitochondria can be damaged by increases in cytosolic calcium, by reactive oxygen species, and oxygen deprivation. Also, mutations in mitochondrial genes are a cause of some inherited diseases as well. Let's talk about an influx of calcium and a loss of calcium homeostasis. So ischemia and certain toxins cause an increase in cytosolic calcium concentration. So this increased calcium can result in an increase of the mitochondrial permeability transition pore and thus impair ATP production. Now, increased calcium can also activate certain enzymes like phospholipases, proteases, endonucleases, and ATPases, which all can result in negative cellular effects. Next, let's talk about accumulation of oxygen-derived free radicals, so also referred to as maybe oxidative stress. So free radicals cause cell damage through membrane lipid peroxidation, through protein modification and DNA breakage, free radical injury. They can also created by a lot of different things. So how do you get those free radicals? Well, radiation exposure, metabolism of drugs, redox reaction, nitric oxide, transition metals, a leukocyte oxidative burst. Now, some of these are desirable, like the leukocytes creating an oxidative burst, because this can be useful in killing bacteria. Of course, radiation would not be a good way to encounter free radicals. Reperfusion after anoxia is another problem. That's going to produce a free radical production. So this is actually a major cause of injury after thrombolytic therapy. So this is why we have windows for thrombolytic therapy. So say in a stroke patient, if you can catch the ischemic stroke within maybe 3 hours, you can go ahead and give your thrombolytic. If it's beyond 3 hours or even beyond 6 hours, you can't do it because of that reperfusion injury. It's going to be worse than doing nothing at all. And even a few anti-cancer drugs can induce free radical DNA damage, and that's actually what they're designed to do, so that's a positive way. Now, because we've been talking so much about free radicals, how do we get rid of them once you have them? Well, free radical degradation is produced through enzymes that we already produce: catalase, superoxide dismutase, and glutathione peroxidase. Also by just spontaneous decay and antioxidants. Now, all of these protect you against free radical damage, but remember the catalase, the superoxide dismutase, and glutathione peroxidase. Important stuff there. So now let's move on to infarction. So what's infarction? Well, infarction is tissue death caused by a local lack of oxygen, and this occurs when you get an obstruction of the blood supply. Now, there is something called red infarctions and pale or white infarctions. So red infarcts occur in loose tissues with a lot of collaterals, things like the liver, the lung, or the intestine, or following reperfusion. Now, after obstruction of a blood supply occurs, that ischemia ensues. Now, there's not enough blood supply for the cells to survive, but there are collaterals that ischemia is going to rapidly follow that reperfusion. And because there is cellular damage, that increased perfusion becomes very, very messy. Blood is kind of leaking into damaged tissue, and it's going to cause that red infarct. Now, the other thing that might happen is if you have an area of ischemia, you don't have collaterals, but that ischemia is there only for a specific period of time, maybe just a few hours. And then the ischemia resolves, maybe it's an emboli that's been busted up by TPA or just got rid of spontaneously, and then you have reperfusion of that area that was previously ischemic. Well, there is definitely going to be cellular damage in that area, and that reperfusion also is going to be very messy and cause a red or hemorrhagic infarct as well. Now remember, we just talked about how reperfusion injuries is due to damage by free radicals. So when you reperfuse an area that is hypoxic, you'll generate a lot of oxygen-free radicals, and those free radicals are going to induce even more damage than the hypoxia had induced in the first place. Now let's talk about pale or white infarcts. That's going to occur in what we call solid tissues with maybe a single blood supply, not a lot of collaterals. Think about the heart, think about the kidney, the spleen, and again, sometimes in the liver as well. Again, if you are not revascularizing these areas, you'll just end up with a pale infarct. All right, guys, that brings us to the end of the video. It's time for that end of session quiz. I want you to stop the video, try to answer those questions on your own, and then we'll go over them together. First question, what histologic features are seen in apoptotic liver cells? Well, you're going to see cellular shrinkage. You're going to see pycnosis, which is where the nucleus gets kind of condensed and the chromatin is all kind of clumped together. You're going to see karyoresis, which is nuclear fragmentation. You're going to see membrane blebbing, and then the formation of apoptotic bodies. Next, what substances do cytotoxic T cells and NK cells use to induce apoptosis in the cells infected with, say, a virus? Well, they're going to use perforin and granzyme B. The perforin makes the holes, the granzyme B goes in and activates caspases. Next, what highly damaging events can cause irreversible cell injury? So think of things like big calcium influxes. Think of damage to the plasma membrane. Think of rupture of the lysosome, mitochondrial permeability, pycnosis, karyolysis, karyoresis of the nucleus, so any type of damage to the nucleus itself. Next, what cellular enzymes are responsible for handling oxygen-free radicals? So we went over this a couple times. Remember, it's peroxisomes that contain things like catalase, which is an enzyme that degrades hydrogen peroxide to O2 in water. Remember that superoxide dismutase. That's going to be a similar thing. It's going to convert oxygen-free radicals to hydrogen peroxide. And then glutathione peroxidase catalyzes free radical breakdown as well. All right, guys, that brings us to the end of our video. I hope you learned something. I'll see you next time. 911, what's your emergency?
I need some help. I'm dying.
Sir, calm down. Tell me what's happening.
All of the cells inside my body are at risk of dying at any moment. There's this thing called BAX, and it can come out of nowhere, and it allows cytochrome C out of the mitochondria. And the next thing you know, a cascade of enzymes are activating caspases. And then boom, cell death.
Sir, I believe you're referring to the intrinsic pathway of apoptosis.
Oh, really? You know what this is?
Oh, yes, sir. We get calls on this all the time. But don't worry, apoptosis is orderly, programmed cell death. It's normal and your body needs apoptosis to remain healthy.
Well, okay, maybe that's normal, but get this. Some of my cells are being threatened with death signals. These death signals can be received by TNF receptors and FAS receptors on my cells. Once activated, these deadly caspases get released again, and boom, death! And if that's not enough, killer lymphocytes are lurking around and they release perforin and granzyme B. That's right, granzyme B. I think I can hear the tiny cries of my cells dying right now. I need some help.
Sir, you've just described the extrinsic pathway of apoptosis. Again, this is normal. This is healthy.
Really? Well, that's a relief. I thought this was going to be a much bigger deal. Thanks.
No problem, sir. Anything else I can help you with today?
Well, it's probably nothing, but I stabbed myself in the hand with a chef's knife while I was cooking earlier tonight. But that's probably just like you said, apoptosis.
Sir, no.